excited to present our science fair project, which is sonar navigation system. Sir, our project explores how we can determine the position of a moving object by using the sound only. The same principle that is used in the applications of the submarines, sonar, the robotics and the autonomous vehicles is used here. And these systems are quite proprietary or military, thus it becomes more expensive, which restricts the team to use such technologies for their project. But our project ensures a solution for this, as we have used some off-shelf parts and which can easily read the code, which becomes more accessible to any team who wants to work in this project by this system. So my next fellow team member, Tolsif, is going to tell about the mechanism of our project.
Thank you, Rahat. Now, sir, I will explain you the mechanism of the project. So, at the heart of our project is a technique called TDOA, or time difference of arrival. So, in this technique, the transmitter, as you can see there, sends a signal towards the machine through the air. And in the machine, the microphones or the receivers pick the signal up. And as you know, sound has a speed. So, each receiver receives the sound at a different time. And by calculating that difference, we can determine the position of the transmitter. This is exactly like how our brain determines where a sound is coming from, by knowing which ear receives the sound first. So sir, let me tell you how it works. There are two microphones or ultrasonic receivers at 2 points of the machine at a fixed distance apart. So the transmitter sends out a signal or a sound pulse which is then received by the machine, and as you know, there's a difference between which microphone will receive the sound first. So it will calculate the difference, and with that difference we can determine the angle of the transmitter, and with that angle and the value of the speed of sound in mind, we can determine the location of the transmitter relative to the receiver. Now my team member Nahiyan will demonstrate the project and explain the details.
Thank you, Iqbal, for giving me the floor. Before demonstrating the project, I want to explain how traditional sonar works in normal system. This is a sonar sensor, HCSRV4. How this works.
Wait.
Yes, sir.
Can you demonstrate?
Oh yes, absolutely. Sir,
On the how sonar works.
So now, here this is the receiver board, and all on the board here, platform, there are 3 transmitter boards, and this is the main board that is all connected. The transmitters use Arduino Nanos, and this is an ESP32S3 program, and this program here uses Python. So now, if I move this one to the middle, you can see that the green line here moves here. It tracks it like this, and if I move it to the side, it does not work if I rotate it because it grows out radially, so the position doesn't change, so it won't register.
So using that saw, you're just receiving the signal.
Yes, we receive the time differences between the signals, and with some trigonometry, we can figure out the angle the receiver is at.
Why the angles are changing?
Oh sir, this is because you see, we do not have, this is because of sampling issue. What happens is the ESP, we are using interrupts, right? This is hardware interrupt, but ESP is not very accurate. We would need things like FPGAs and so on to have a very accurate. So we are using what we can, and with this we can show at least the general direction of our project. Now, getting back to this, so we can show the relative angles of each of the transmitters. I say relative because if I move the receiver board, all 3 of the lines move
You
in.
remove the transmitter part from that two source.
Yes, so it doesn't
Just
interfere.
using the
Yes, just
For
receiver.
these two, it's only the transmitting or the receiving board.
See, the sonar sensors, they can transmit without having to receive the signal. So we didn't modify those ones. But these
But
ones
you
we
can
need
move
some.
one sensor from this.
Yes, yes sir.
If you can move one of them from
Yes, you can move and it
This
moves.
will work.
Yes, it will work.
Okay.
So now, so we know the angle of each of the transmitters, but we need to know the absolute position. For that, what we need to do is we need another receiver. And let's say here is another receiver. Now, one receiver will say the transmitter is at this angle, and another receiver will say the transmitter is at this angle. The intersection of these 2 angles will be the actual position of our transmitter here, and that is a technique called trilateration. The more receivers we have, the more accurate this gets. And now, this project has been in work for many months, and this is the many prototypes we had fixed. For example, this is the original receiver board we had wanted to use for the science fair. It had much longer one. And then we also, before using the commercial boards, we wanted to make our own boards here. So you can actually see them if you want to. These are custom-made PCBs. We made this ourselves. And now, what I wanted to get to is that you see these boards, these get tracked automatically as you see here. Now this all works as is. Now, this all works as this, but now let's talk about the real life uses of this.
So what is the practical using?
Yes, sir. I was just getting to that.
Okay.
So now we can think of three immediate practical uses. One of them is pathfinding for autonomous vehicles. Now, autonomous vehicles, what do they normally use? GPS and optical cameras. GPS requires clear access to the sky to use, and optical cameras require light. Now, think of in non-ideal situations or emergencies. Let's say there is a fire. You cannot see anything with a camera in the fire, and smoke is obscuring from the sky. So, what we propose is that in these situations, in this emergency situation, what you do is you spread out these transmitters. Now, these transmitters, these are quite big. We soldered them ourselves. All the boards are soldered. But if you want to, you can shrink the transmitter down very small and spread these out throughout an area. And you put each of these receiver boards onto an autonomous vehicle of your choice. So now, what the vehicle can do is that it will know its relative position to each of the transmitters by the TDOA calculation, and then it can navigate the space as it wants to. And that is how we are proposing. And another one is object surveillance and tracking. That is number 2. Let's say you have a large area you want to track objects in, and you have small boxes or whatever in a warehouse, factory setting, wherever. What you do is you set up a few of these receivers throughout your room, because more receivers, more accuracy. And then you put a small transmitter on each of the objects you want to track. What then you can do is you can track individually all of those objects in lifetime, like we are doing here. All it is a single pulse. The ESP is sending to the Arduino a 1,000 microsecond long pulse, and that is telling the Arduino to activate the pulsing. That is how that works. And now this does not only track objects. For example, for civilian safety, let's say you want to do a large area, let's say you cover a large field or a footpath or whatever with these receivers. Now, what a civilian can do is they can put a small transmitter on their body, bag, waist, wherever. And now, due to the safety net, we will know where their position is at all times. Their family will know whether they are safe or not. They are in the spot or not. Their country will know whether the civilians are safe. And now, this is consensual. This is not spying or anything, because they can just simply turn the transmitter off and it will work. And the third one is coordination for vehicles and drones. Drone swarms, what do they require? The GPS or optics, again, covering them does work sometimes doesn't. So, GPS or optics, again, not always reliable, but we are using sound. So as long as we have a medium for the signals to go through, we can get a reading on our sensors here. Now, sonar is an old technology. It is a military technology mostly. Matter of fact, while researching for this project, I went through many old military patents even from the USA, 60s and 70s. So they were helpful. I knew how to make the flowcharts work and whatnot. So, but this technique does not belong to civilians mostly. It's either very proprietary hardware or military hardware, which they cannot always get access to. Small teams which would, maybe don't have the resources to buy from the big companies, they cannot use such a wonderful technology in their works. And another example, Google Pixel phones, the new ones, they have a feature called SOLI. What is that? That is a sonar radar they use for 3D mapping of objects. But now, that is a 1,20,000 taka phone. Not every team can just buy a phone to use in their project. But they can use something like our project here and fit it to their use. Our project is done very simply, it's open source as well. Every part you can buy at a decent robotics shop. So any team can use our work in their project free of cost and only with sourcing the materials themselves. Now, not only small teams, but the government can use this. As we said with our civilian safety net example, the government itself could implement our situation and confirm the safety of the civilians as they want it, and strengthen our national security as a nation. Now, if you want to, I can show you the different codes. Yes, sir. Now, my team member Ifat will conclude the project and give emphasis on what I have said.
Would the person here is expert in Python?
Sir, all I can express. Yes, sir.
Can I Nahiyan for giving me the floor. Sir, although it is a simple setup, but the technology behind it has powerful real-world applications. Firstly, it can be used for rapid setup for emergency or autonomous vehicles. In places where GPS fails like tunnels or collapsed buildings, vehicles can use a system to navigate safely. Secondly, it can be used for indoor tracking for safety and automation. People or packages carrying small ultrasonic sensors can be tracked inside buildings using just a few fixed receivers. This is useful in places where security matters. And thirdly, it can be used for cooperation of multiple robots. In shared places like factories or warehouses, robots need to know where others are so that they don't collapse. By giving each robot a transmitter, their location can be tracked using only sound. So, what makes our approach valuable is that it's compact and affordable, and it uses only sound and timing to operate. In conclusion, our project shows how TDOA can accurately estimate the position of moving sound source. That's all from us. Thank you.